Hi everyone. So our next talk will be given by Stephen Miller and Wael Khateeb on predators and policies, teaching ODEs by modeling Florida's alligator ecosystem.
So thank you very much for the invitation. We're thrilled to be here. This is one of my favorite conferences to go to. I just wish I had more time to listen to all the talks. Unfortunately, since I'm home, too many things to deal with. I want to talk a little bit about the Polymath Junior program, which is the framework for the work we were doing together. And so if you have any questions about it, we're happy to chat more either at the end of our talk now, or you can, contact us. We have our email addresses up here. So if you could advance the slide. There you go. So just to give you a sense of what we're going to talk about. So the Polymath Junior program was created during the start of the pandemic response, when a lot of opportunities were drying up for students to do research over the summer. And it worked so successfully that we've continued it since then. And I'm hoping that some of you who are listening today will be interested in learning more and hopefully running groups with us next summer. In fact, this is how the two of us met. I was presenting some work I had done with some students, and we found out that we had some similar interests. So after describing what the program is like, we'll talk a little bit about the importance of getting to know who is in your team, and then trying to figure out what's a good research project to work on. And so people have very different backgrounds, they have very different freedoms and commitments. What we're going to do today is trying to focus on problems that are accessible, that will make a difference. And then we'll discuss briefly some of the methods we were using and some of the results, collaborations we formed. We're now actually talking with experts in a variety of fields. And then we'll talk about future steps and some lessons learned. So let me talk to you a little bit about what the Polymath program is. So the Polymath program was, oops, can you advance the slide? So the Polymath program, you can scan the code. My co-author was kind enough to put that out there, covers a huge variety of different areas. So we have everything from pure mathematics to applied mathematics. We have machine learning. We have lots of different areas. And the goal is to try to provide research opportunities to undergraduates who wish to get a sense of what is it like to do research, as well as to provide opportunities to graduate students and junior faculty as to how do you create your own research program, how do you start mentoring people in doing work like this. So thank you for whoever just posted, Tova, for posting that link in the chat. And so let me talk a little bit about the details and the mechanics as to how the program works. So it is entirely online. And oops, can you advance the slide? So it's entirely online. We have been able to give acceptance to almost everybody who has applied over the years who is a college student. And because it's entirely online, we don't have to worry about obtaining funding for everybody, which is both good and bad. We don't have to worry about people being free to work on it exclusively over the summer. They can have another job at the same time. We do have the challenges of people working in many different time zones and having different amounts of freedom, also different amounts of background. So there's a lot of mechanical issues to deal with to make this work successfully, but the benefit is we can deal with hundreds of people working on research projects over the summer, as opposed to on the order of 10 to 30 in a standard program. One of the important aspects of anything like this is the ability to scale it up. And so rather than just having, one or two people running groups, we try to get a lot of grad students and postdocs and junior faculty involved so that in the future they can run their own group. Several people who have worked with me are now running their own group, which is absolutely wonderful. So we give a lot of training to graduate students and junior faculty on how do you create research projects, how do you find things that are accessible, how do you do enough work to get a sense of what is going to be doable, but not so much that you've taken away the fun for the students of being the ones to discover things. And so again, if anybody here is interested in finding out more about this, we're always looking for graduate students to help with the mentoring, junior faculty to help suggest problems, and if there are undergraduate students who are listening, we are looking for people to actually solve the problems that we come up with. And so to date, we've always been able to give people one of their top choices for advisors. We have little mini lectures that we deliver to everybody so that people can get a sense of what might they be working on and then choose accordingly. We have the deadline as April 1st to apply, so that if you get into a standard program, you can do that instead and not be put in a pressure situation. So I'm going to turn it over now to my colleague.
Thank you, Professor Miller. And thank you, everyone, for joining us. So I'm going to start with introducing our team. So we started with Jasmine and Jesse. Jasmine is a student at University of Nebraska-Lincoln, and Jesse is at Rutgers. This is our initial team that we started with. And I am the mentor of this project. And of course, Professor Miller is the supervisor who's making sure everything stays on track. And recently, we have two new data science students who joined our program, Anne and Sangam, and both of them are from the University of Toledo. So let me give you guys a bit of background about what I do for a living. My background comes from modeling predator-prey models and high codimension bifurcations. We look at codimension 2, codimension 3, sometimes codimension 4 bifurcations. We look when do we have 2 limit cycles, when 3 limit cycles. And we even try to come up with a new normal forms. So this is part of my dissertation. I also have some experience with machine learning, physics-informed neural network, and so on. Nonetheless, my work has been, despite dealing with predator-prey models, SIR models, it has been very theoretical. And I said, well, I want to try to scale this down, try to take these skills and actually apply them to some of the models and apply them to some of our real life challenges that we're dealing with. And from there, we said, okay, we have 6 weeks for Polymath Junior to run. And we started with Jesse and Jasmine. And surprisingly, Jesse and Jasmine didn't even know differential equations. So we had 6 weeks to prepare Jesse and Jasmine. We knew that it's going to be a tough job to do, but at the same time, we wanted to come out with at least some results or have the project well communicated between the members by then. So we set some standards, we set some rules how to deal with things. First of all, we wanted the communication parts. Between me and Professor Miller, we use emails like chat almost. It's 30 minutes, whether it's a Friday evening, a Sunday morning, we're always on the emails chatting. How can we improve things? How can we work on things? Second of all, we knew that we cannot teach differential equations and do research at the same time within 6 weeks. So we have to restrict the material to things that the students actually care about or will end up using. And we said, okay, we're not going to share everything. Let's say we introduce students to the basics, the things that we think they're going to use. And if anything new they need to learn, we'll bring that up by then. Third of all, we wanted weekly group meetings. During the 6 weeks, we had 2 to 3 meetings per week. After that, we decided to keep going with the project. We're still meeting weekly, sometimes twice per week, and sometimes I have office hours for students to pop in and ask questions. And then finally, we want to make sure that students are enjoying the work. We want to make sure there is a positive reinforcement and motivation so that they take ownership of this project. This project isn't ours. We know how to do all the math, but we want the students to feel proud of their work. And I think that was a key part to why the students are still working with us till now. So let's start with this. This is the logarithmic growth for, let's say, the x by dt here. Let's say X is the population. We had to introduce it in a nice way that would grab their attention. So we said, okay, assume you guys, this is zombies. X is the population of zombies, and K is the number of human beings out there that they can eat. So we took this model, we said, all right, let's try to graph it. What do you guys notice? Where are the orbits approaching? What's going to happen if our initial conditions is changed? And so on and so forth. And from there, we were able to link the derivatives with the actual population numbers, the actual number of zombies, the number of human beings available, and so on. Now, the next part was bringing up a calculator. So we said in one of the meetings, all right, guys, let's say you have 3 functions, f1, f2, and f3. Okay, out of these 3 functions, let's compute f1, f2, and f3 at x equal 100, x equal 1000, and x equal 10,000. What do you notice? And the students will go like, okay, well, we noticed that f3 grows the largest. And f3 is kind of dominating over the remaining 2 functions. It's skyrocketing in terms of the values of the answer of the function compared to f1 and f2. So now we said, all right, what if we do the exact same test, but let's flip things around. Let's take x very close to 0. What do you guys notice? So they plug in 0.01, they plug in 0.001, and then they plug in 0.0001. And then they started noticing that, well, you know what? The function that has the lowest exponent is the one that's going to have the largest value. Okay. Well, if we think that near the origin, near zero, the lowest order terms are the terms that are dominating here. These are the terms that are actually making a difference compared to the higher order terms. What do you guys think in the right-hand side of an ODE? What do you guys think is going to be the most important term? And then their answer is going to be, well, of course, it's going to be the linear term, the one that has the lowest exponent. And from there, we said, well, congratulations, guys. That's the Hartman-Grobman theorem. That's how we introduced it to them. All right, so one part is getting to know what an ODE looks like, another part knowing the linearization part, and then the third part is being able to graph them. And given the 6 weeks limit, we said, all right, there's no way we're gonna be able to show these students how to code and how to use MATLAB and use everything from scratch and introduce them to Python. So we said, all right, you know what, guys, there's a couple of already built-in, well, let's say well-maintained libraries in MATLAB where you can plug in a system of 2 differential equations and you can have the orbits well drawn, and that system software is called P-Plane. It's available online. I think it's free. So go ahead, let's experiment with this. And then afterwards, okay, now that you enjoyed, what if we have 3 equations? Well, P-Plane only accept 2 equations. Then here's an ODE 45 code, that a code that uses ODE 45. What I want from you guys is let's try to understand this code. And if you want to change the equations and the parameters, which parameters do you think you should change? So instead of having them write the code from scratch and getting their heads banging on the walls, we provided the code, but we told them, try to understand what each line is doing, try to understand the differences between this code and so on. Finally, we went into bifurcation theory. We said, all right, this is a system of differential equations. Let's use P-plane again. Well, let's set R to be a positive value. What do you guys notice? Well, we noticed that there's no equilibrium points. The orbits are just going to keep going to the right. And then I told them, all right, let's set R equal 0, and then let's set R equal -1. And then they started noticing, okay, well, the three cases, they seem to be different. What's actually happening here? And the answer was, this is what we call bifurcation. This is a change in the way the orbits are going to act near equilibria. There's the change in the number of equilibria and the stability of these equilibria, and so on and so forth. Now I ask the next question, what do you guys think? How many parameters are we changing? And then they said we're changing 1 parameter. All right, we call it a codimension 1 bifurcation. What do you guys think if we change 2 parameters? What's going to happen? Then that's going to be a codimension 2. And from there, we started introducing other bifurcations, Hopf, and so on. Now, there's certain meetings where students can't be always prepared. We have certain weeks where some of my students we had an exam, we had 3 exams on Monday, we had quizzes. Sometimes they actually don't have anything to present. And a part of this project isn't just getting a paper out. We genuinely care. Of course, we care to get the paper out to make sure that their work is noticed. But most importantly, we want to actually prepare them for graduate school. So we said, all right, you don't have anything? That's okay. Let's use this session to learn. How about we introduce you guys to delayed differential equations in this session? What we're going to do, Dr. Miller and I, we're going to give you 20 minutes on the spot. Go ahead, use whatever AI tools you want, whatever techniques you want, Google it. But within this 20 minutes, when we come back, we want to see a very small presentation of what you learned about differential equations, about delayed differential equations. And they use think pair share. They use these techniques of discussing between one another. And then within 20 minutes, they come back with some idea about delayed differential equations. And then we complement this knowledge with what we know. We did the exact same thing for reaction diffusion models. We introduced them to Turing bifurcation this way, where, of course, not every week they're going to have something to present, but at least every week we can get them to learn something new, or every other week to get introduced to different parts of dynamical systems. Now we get to the actual project. The actual project goes around modeling of Florida's alligator population. So back in the 1800s, there was intense hunting for these alligators, and the population actually really dropped. In the 1950s, 1960s, Florida stepped in. They set some very strict regulations regarding harvesting. They said the number of harvesting per hunter per season cannot exceed two. And eventually, the alligators aren't anymore endangered, and they are relatively safe. Nonetheless, this brings us to the next problem, which is, oh yeah, over here there's the FWC, the Florida Wildlife Conservatory, I think. It gives lottery permits, so 2 alligators per permit per hunter per season, and they make sure every alligator is tagged and they have all the details about where they found him and so on. Now, the problem is in the 1980s, some rich people most likely got Burmese pythons for fun for their own private collections. And they decided they don't want these pythons anymore. They released them in the wild. We're estimating the starting point of 5 Burmese pythons. Right now, we have thousands. We don't have an actual estimate. Nonetheless, these Burmese pythons, they kind of feed on the same prey as the alligators. They are both competing, pythons and alligators competing on the same prey. The number of raccoons in the Everglades in Florida dropped by 95%. So this is how big the actual issue is. So the economical implication was a sharp decline in mid-sized mammal, and this is a big competition between predators, the alligators and the pythons. And which brings us to this. Well, we want to model this interaction between all these species, the prey, the pythons, and the alligators. And we said, okay, let's do that through predator-prey models. I'm going to go really quick over here. I think I'm almost out of time. But the thing is, we can do a lot of alterations to this model so that we make it suitable for what we are dealing with. And accordingly, we said, all right, let P0 be the general prey, P1 be the alligators, juvenile and adults, and P2 be the pythons. And from there, we decided to put together this model. We used linear functional responses to keep it as simple as possible, especially when the number of equations goes up, the more complicated the problem becomes. And finally, we said, all right, you know what? We don't think constant harvesting is going to do it, as that was going to make the system, the positivity of the system not guaranteed, especially here in dp2 by dt, the minus h2, because it's a constant harvesting and we're limited to 2 alligators per season. This is going to make it tough to model. So we said, okay, let's use some kind of like a functional, Holling type functional 2 response for the harvesting. It's a saturated harvesting. That is going to make sure that this term remains positive or at least approaches 0 when the number of alligators goes to 0. And that solved the problem of positivity. So at the end, we ended up reducing the model to 3 equations as follows. This is our final model. And in total, we have 7 equilibria. Now, the system is a very interesting system because in the absence of pythons, we end up having a limit cycle, we end up having a cyclic behavior. And from there, we said, okay, what is causing the formation of the limit cycle? And we said, we noticed that eventually we have a Bogdanov-Takens bifurcation, which is kind of Hopf and saddle node combined together. And the way to do this is the students have to go through a series of 5 steps to translate the equilibria, find the normal form, center manifold theorem, finding the Jordan canonical form, and so on and so forth. But recently they're done with this step, and we're happy that they have the normal form. Now, the whole target of the ultimate goal of this project is we want to analyze the relation between Burmese pythons and alligators. Can we use bifurcation theory to see when does the system when is the system stable, when it is unstable? Is introducing these pythons, do we need to adjust the harvesting policies that Florida implemented? Should we keep the harvesting at 2 alligators per season? Should we lower it? Should we increase it? How is introducing the pythons into this ecosystem, actually leading to changes in the policies. And that's the ultimate goal. And from there, this is more simulations. From there, we ended up modeling the interactions between the harvesting of the pythons versus the harvesting of the alligators. And we noticed that the coexistence region, where both predators coexist, is a very thin region, which means that the regulations for the python removal and the regulations for the alligators removal has to be adjusted very carefully here. Finally, we reached out to the University of Florida. We have a couple of ecologists who are interested in our work, and they agreed to send us data, and we are hopefully now in the process of taking this project a step further. And we're very grateful for their support. We also have two data science students from University of Toledo, Anne and Sangam, that I introduced, and they're going to be taking care of the data and graphs of our project. We took our students to the Scion Texas LA conference, which is a research conference, and Professor Miller and we presented this work further at JMM. And I want to take this opportunity to thank Polymath Junior, because genuinely Polymath funded this project. It funded our trips. It helps us get the exposure that we need. It helps us talk to the University of Florida. And for that, I also want to thank Professor Miller. Wrapping notes, just need one quick minute. I want the students to take ownership. I want to provide opportunities at every possible corner, and I want them to actually enjoy this work. There is no pressure for publishing. There is no pressure of we have a strict deadline or any of this. This is a project that, as long as they're happy and excited to work with, I'm happy. Thank you so much. And I want to wrap up with one thing. I'm on the job market, so if anyone knows of any open position, please do let me know, and I'd be more than happy to apply. Thank you so much for attending our talk, and thank you for Simiot for organizing this talk. Thank you so much.